and that's our
So you
derivative.
just merge them together?
What did we merge?
Just like basically take the multiplication down because there's really nothing you can do with them?
Are you talking about this part?
Yeah, because you're supposed to multiply them together, but there's really nothing that you can multiply together. So do you just merge them together and just kind of put them side by side, or is there something else that we can do with that?
Right, so there's nothing else we can do. We can only multiply things, so my internet is unstable. We can only multiply things together if they have the same base. And so since we have a 4 here and an X here and an E here, those don't multiply at all. So
Okay.
all we can do is leave them to be multiplied together, which is what they're doing here. So this is the product rule. It always is used when we have a function that is the product of two functions. So x to the 4th times e to the x are each their own function. And so since they're being multiplied together, we have to use the product rule to take their derivative. On something like number 1, we could have FOILed this out and just used the power rule when it's in its polynomial form, but we can also use the product rule. Either way works. So 3.3 is about derivatives of products and quotients. So we also have a rule for quotients called the quotient rule. Quotient rule is a little bit less nice than the product rule. And it is on page 198. So here, instead of having two things multiplied together, we now have two things being divided. So just like F and S were first and second for the product rule, in this case, T stands for top and B stands for bottom. So that's why the two parts of this function are T and B. So we have f of x equals t of x over b of x. So this is just any kind of quotient, any function that has a numerator and denominator. Then the derivative is this whole thing. This is another one that you will be given on the test. So you don't have to memorize this. You are more than welcome to memorize it. But the important part is that you know how to use it. So I'm going to go back for just a moment to our product rule. Product rule is all multiplying and adding. So there are ways that we could rearrange this and make it mean the same thing. Because we know if we have multiplying, we can switch them around. If we have adding, we can switch them around. It means the same thing. The same is not true for the quotient rule, since this is all dividing and subtracting. It's really important to get every single part exactly right. We can't move anything around here. So the quotient rule is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So we're going to do the same type of thing here where we're going to identify the top and bottom first and each of their derivatives. So we have those 4 parts, then we can put all of it into the formula. So here is our first example. So what is our t of x here?
(3x minus 6).
Yes, exactly, 3x minus 6. That's the top. And how about our b for the bottom?
X squared plus 1.
Right, exactly, x squared plus 1. So we're just taking the top and the bottom and calling them t and b. And just for room, I'm going to put t prime and b prime down here. So now we need the derivatives of each of those. So what's t prime?
3.
3, yes. And b prime?
2x.
2x, exactly. So that's our power rule in action. So now our job is to put all of this into the quotient rule. I'm going to rewrite the quotient rule down here, and I'm just going to write it in shorthand with just b's and t's and not the x's, just to make it a little shorter. So we're going to have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So quotient rule gets a little messy after we plug everything in, but from here, all we're doing is algebra. Plugging in some expressions into some places and simplifying. So we have f prime of x equals the bottom, that was x squared plus 1, times the derivative of the top, 3, minus the top, 3x minus 6, times the derivative of the bottom, 2x. And that's all over the bottom squared. So that was x squared plus 1 squared. So we identified our t and b. We took the derivative of each of those, and then we just plug in those 4 parts into their positions in the formula. Now we have to simplify. Simplifying just means to simplify the numerator if there is something to do, which there is here. We can distribute so we don't have these parentheses anymore and combine like terms. There's no reason to FOIL out the bottom. So we would leave the bottom in factored form. So on top, we can distribute that 3 first. On the bottom, or not on the bottom, on the other side of the top, I'm going to do this in 2 steps just to show that we have to be super careful here. So we have a minus sign in front of the 3x minus 6 times 2x. So we can first distribute that 2x in. So we have 6x squared minus 12x. But that minus sign is applying to everything that comes after it. So we do have to make sure that we don't just get rid of those parentheses when we distribute the 2x. We also have to deal with that minus. So on top we have 3x squared plus 3 minus 6x squared plus 12x. Go away for a minute. Thank you. And now we just have to combine like terms on top. Most of the work on a quotient rule problem is the simplifying steps. The taking the derivative part is pretty much the same as the product rule, identifying those 4 things and putting them into the formula. Quotient rule problems can be kind of long, like we're seeing here. But don't be intimidated by them being long. We have the formula that will always be what we use for a quotient. We have to find t and b and t prime and d prime. Once we know those, or t prime and b prime, once we know those, we can put them into the formula and simplify. Any questions about that one before we do one more quotient rule?
I just had a quick question. If is there going to be any time that we would factor that out, the bottom, so that we could cancel some things out, or we always do it like that?
So we would never FOIL the bottom out. If there were stuff to cancel, we would, but that would entail factoring the top and leaving the bottom as it is. So in this case, we could take out a 3 from the numerator. A -3. And that would be fine to see if there's going to be anything to cancel, but there's not in this case. But if we're going to check to see if we can cancel, the denominator should stay as it is because that's in its factored form. We would have to factor the numerator and then see if there's anything that will cancel between the numerator and denominator.
Okay.
That's unlikely to come up, but it's always good to try to reduce fractions when we get them as an answer. this. Yeah, that's right. Okay. Thought I had a typo in there, but that's correct. Okay, so this is our next quotient rule problem. So take a minute to try to identify T and T prime and B prime. Okay, what is our T and T prime here?
2x and 2.
Yes, exactly. All right, and what is our B?
1 plus natural log x.
Yes, exactly. And then what's our B prime?
1 plus 1 over x.
Almost.
Would it be 2 over x then?
Just
You're-
I
one
just
X.
got 1 over X.
One
Yeah.
X.
Just 1 over x, exactly. So that natural log, derivative of natural log is the 1 over x. That 1 just goes away since that's a constant, the 1.
Oh, okay.
So these are our 4 parts. So now our job is to plug them all into the formula. Which is prime, T prime. Yes. So we have our bottom, 1 plus ln x times T prime times 2 minus the top, 2x times B prime, 1 over x, all over B squared. So 1 plus ln x squared. So that's the taking the derivative part. We found our 4 pieces and put them into the formula. Now we just have to do a little bit of simplifying. So we're always going to have that bt prime minus tb prime. So those 2 parts will multiply together if there is any multiplying to do, and then we can deal with combining like terms if there are any. So in our bt prime part, we have the 2 that can distribute. So we'll have 2 plus 2 ln x minus this next part, we have 2x times 1 over x. So those x's just cancel out. And lastly, those twos on the ends of the numerators cancel. And that's our derivative.
Quick question, when we're doing the homework, because as we're going through the line, can we just put the answer and then the equals the f prime of x?
You mean put f prime like over here?
Yeah,
That's fine.
okay.
It's a little weird looking, but not problematic.
Okay.
So these are our product rule and quotient rule. Most of the work is just the simplifying algebra part. Really, the only calculus thing is doing that t prime and b prime at the beginning and then plugging them into our formula.
Hey, Madeline,
Yes.
I missed probably the first like 7 to 10 minutes of class, and I'm curious if what we're going over, does the quotient rule is what we just did, right?
Yes.
In example 1 and 2, and then the product rule has the same formula, or no?
No, but that was the first thing we did, but it's a similar-ish formula. This is the
Okay.
formula.
All right, let
And
me
that
just
was
write
on
that
page
down. Thank you.
196 of the book. Yep.
196, perfect.
Yeah, they're similar in that we're always looking for those two like starting parts. In the product, it's first and second. In quotient, it's top and bottom. And then we need to take the derivative of each of those parts. It's just the formula we're plugging them into is different. So we have sorry, I just saw the time and I can't believe that it's already 12:15. That sort of stunned me for a second. So we have a handful of derivative rules so far. And I just want to take a moment to sort of make a list of those. And I'm going to make a sheet for chapter 3 also with these rules. So in chapter 2, we had a handful of rules like the multiplying by a constant rule and adding and subtracting, which I don't necessarily want to list, but sort of the key things are the power rule. That was what we did in chapter 2. We have our exponents rules. And I'm not writing these out right now because they're in the book and in your notes and in our class notes, but these are what we have done so far. So we have power rule, exponents, logarithms, and we just did the product rule. And quotient rule. And we saw that when we're doing the product rule and quotient rule, we have to use the other ones when we're finding that f prime and s prime or t prime and b prime. But these are each their own rule. Our last rule, can I say that confidently? Yes, our last derivative rule is called the chain rule. And that's what we are going to be focusing on most today. The chain rule combines all of the other rules. So we need to know everything else in order to use the chain rule. And so each of these is for a different specific kind of function. So our power rule is just for things of the form x raised to a power. Exponents are things with x in the exponent, logarithms. And we just saw our product and quotient, which are things that are products or quotients. Our chain rule is for compositions of functions. So we're going to do a little bit of review / practice first with compositions of functions, and then we will learn the chain rule of how we can take the derivative of those things. So section 3.4, the chain rule. Here is a little review definition of a composite function. The letter M is unimportant. I just use that because that's what the book uses, but it could be called anything. But a function M is a composite of functions f and g if m of x equals f of g of x. So we did review of compositions of functions in chapter 1 when we were doing our algebra review to get ready for calculus. And so a composition of functions is going to be, or composite functions are what we use the chain rule for. Anytime we have a function in a function, we have to use the chain rule. So before we get to what the chain rule is, we're going to do a few examples identifying a composite function and what its sub-functions are. So here's our first example. So I'll give you a moment to read that and take it in. Okay, so our instructions are to write each of the following functions as a composite of two simpler functions. So what that means is that we want to find f and g such that y equals f of g of x. So that means that this cube root of 1 plus x cubed should be the composition of two functions. And we want to know what those two functions are. So a composition of functions always means that there's some sort of like nesting happening in a function. We have sort of an outside function and an inside function. So g is our inside because we're being asked to find f of g of x. So what do you think g is here? What is our inside?
1 plus x cubed.
Yes, exactly. 1 plus x cubed. That's what's happening on the inside. So what is f of x?
The cube root of x.
Exactly. Cube root of x. So our outside, the f, is whatever's sort of on the outside. So if we're like going from the outside in, looking into this function, the cube root is the first thing that we hit. So that's the outside thing, the cube root. And x is really just a representative of whatever we're plugging in. So the whatever we're plugging in is the g of x part, which is the inside. So when we look at a composite function, we want to be able to see these layers of the function, our exterior part and our interior part. And we can
Quick
always,
question.
oh yes.
Where does that x come from underneath the square root?
So if we're doing a composition of functions, the x is really just a placeholder to say whatever we want to put into this function is going to be going in for x.
Gotcha. Okay.
And so we can always check this if we're doing this kind of problem, which you won't actually have this specific kind of problem on your homework, but we have to be able to see these layers. We can always check to see if this works by taking the f and g that we just found and doing the composition. So g is 1 plus x cubed. And so if we put 1 plus x cubed into f, f is the cube root of whatever we're plugging into it. And that worked. We got back to what we started with.
Okay. Thank you.
Mm-hmm. Oh yeah. So we want to do the same thing here, f of g of x. We want to identify f and g. Ones where we are doing or dealing with an exponential can sometimes be tricky.
Would it be 50x for f of x?
That is one way to do it. 50x for f of x, and then what would g of x be?
E negative to the power of negative 2x.
Yes, exactly. So that would work. That is one option. We could just take that whole e to the negative 2x and put it in for the x in f.
I did it a different way.
How did you do it?
I did f equals 50 e to the x, and then g of x equals negative 2x.
Yes, that also works. So it is possible on this, ooh, oh, sorry, I got stuck. It is possible when we're doing these decompositions, that's what this is called, that there's more than one possibility. I actually want to highlight this second one because when we are using the chain rule, which is what we're about to do, this one is going to be easier. So our goal is going to be to get simpler functions which we know how to take the derivative of. And both of these things are things that we know how to take the derivative of, which is the goal. Okay, I want to do one more of these decompositions, and I'm going to put this one in. Yeah. Wait. Yes. Okay, sorry. I'm going to put this one in the chat as one of these spot checks, just to see if we're on the same page. So we have the same question here. We're looking for f and g so that they compose to make our starting function. So go to that link in the chat and try to find f and g like we were just doing.